This is lecture 15, example 3. Very similar to the previous example. Once again, not the most useful thing, but if you understand this, you really understand how I/O is done on the RISC-V. And so essentially, what I'm doing here is, we know the memory map associated with the normal RISC-V, but what I'm saying here is that I redesigned it, and now I have a new memory map. Essentially, I have a bigger effective memory. So if you remember, the last one was just 00000 to 0000FFFF. Well, it's actually much bigger. That's 4 times as big now. Essentially, I've added, it's essentially 18 bits and not 16 bits. And so that's what this problem is saying. And so I want to redo this problem and ask how many, now that I have more address space dedicated to actual memory accesses, I want to know how that reduces the ability to input unique bits. And you're going to see it drop down. And the notion is that the address space is shared between memory and I/O, and suddenly we have more memory, so it's going to make sense that we're going to have less I/O. And so the notion here is we still, for input, we'll do input first, we still have input that's a maximum of 32 bits at a time, but it's a question of how many chunks of 32 bits we can get. So this is 2 to the 5th, which is the 32, and this is going to be times something. And so we went, the complete address range, address space for the RISC-V is 32 bits. We've dedicated 18 of them now to actual memory accesses, which leaves us only a 14-bit range for the input and the output. And so this is going to be 2 to the 14th, with the notion that 14 plus 18, this is memory, and this is I/O. This is the memory space, total memory space divided between memory and I/O. And the result is going to be 2 to the 19th. Still quite a few. I think that's half a meg or something like that. Still quite a bit. But the notion is I want you to understand where this came from. Typical question I ask on the finals, and way too many people always miss it. Okay, so the same thing with output. Generally speaking, you can practically see it's going to be the same. We get this many, the outputs are this many bits wide, and it's a question of how many we get. And so it's going to be 2 to the 5th, which is the width of this thing, times the address space dedicated to I/O, which is 2 to the 14th. So this again is going to be 2 to the 19th. Okay, quite a bit there. So both the same. So once again, summarize this. The input has a mux in front of it. The control signal, the select inputs for that mux are the address, and so we're really care about address space in this. Same with the output, or similar anyway. The address is now an input to a decoder, we'll say. Output is going to enable one of these registers, and so the output is 32-bit wide, and we can use 14 bits of that address for I/O. And that's all I have for this problem.